Ever stop and think about how anything, can travel across the entire globe at the speed of light? It sounds like magic, but it's actually a principle of physics that is just as cool. Today, we're going to dive into this amazing phenomenon called total internal reflection. It's the science of literally trapping a beam of light.
So that brings us to the big question, the one that makes pretty much all of our modern communication possible. How in the world do you capture something as fast and, well, as straight as a beam of light, and then get it to bend around corners?
You know, the answer isn't science fiction. It's actually hidden inside the thousands upon thousands of miles of optical fibers that are the backbone of our internet. The secret sauce they use is a powerful principle called total internal reflection. So let's break down exactly how it works.
To really get how light gets trapped, we first need to understand the number one most basic rule of the game. Okay, so here's the crucial part. Total internal reflection can only, and I mean only, happen when light is traveling inside something like water or glass, and then it hits the boundary with something less dense, like air. The key is, it has to be trying to get out.
So what do we even mean by denser and rarer when we're talking about light? Well, it all boils down to the speed of light. In a denser medium, like water, light actually slows down. We measure this with something called the refractive index, which we call n. So a higher n just means it's a denser medium, and light moves slower. On the flip side, in a rarer medium, like air, light speeds back up, so it has a lower refractive index. Just lock this rule in your head. For this whole thing to even have a chance of working, light must be going from a high-n material towards a low-n one.
Okay, so with that first rule in our back pocket, let's walk through a little thought experiment to see exactly how and when light gets trapped. It's pretty cool.
All right, let's set the scene. Imagine we've got a little light source at the bottom of a pool at point A. That's our denser medium, the water. And it's shining rays of light up towards the surface, trying to escape into the air, which is our rarer medium. Now, to keep track of our angles, physicists use an imaginary reference line called the normal. Just think of it as a line drawn straight down, perfectly perpendicular to the surface. You'll see why it's important in just a second.
Okay, let's follow these light rays one by one. Ray A01 hits the surface at a pretty small angle. It gets out, no problem, but notice how it bends away from that normal line. That's just standard refraction. Now look at ray A02. We're increasing the angle, and you can see the escaping ray bends even more sharply. Then, with ray A03, something incredible happens. We hit this perfect, precise angle where the ray bends a full 90 degrees and just skims right along the surface. It can't quite get out. This exact tipping point is called the critical angle. So you gotta ask, what happens if we push that angle just a tiny bit further, like with ray A04? Well, the light just gives up trying to escape. Refraction is totally impossible. Instead, it reflects perfectly back down into the water, as if the surface of the water just turned into a flawless mirror.
And that phenomenon right there is total internal reflection. It's that moment when 100% of the light gets reflected back into the denser medium. No light is lost. It is, for all intents and purposes, trapped.
Now that magic tipping point, the critical angle, it's not random at all. It's a very specific physical property that all depends on the two materials touching at that boundary. And get this, we can calculate it with a beautifully simple formula.
And here it is. The sine of the critical angle, which we call IC, is just the refractive index of the rarer medium, N2, divided by the refractive index of the denser medium, N1. It's that simple. Just remember, it's always the smaller number divided by the bigger one.
Now this is where it gets really interesting, seeing how this all plays out with real-world stuff. So for light, trying to get from water into air, we'd calculate the sine of the critical angle as N2 over N1, which is 1.00 for air, divided by 1.33 for water. If you pop that into a calculator and take the arc sin, you get 48.75 degrees, exactly what's on the table. But check out diamond. Its refractive index is massive, 2.42. And that gives it a super tiny critical angle, just 24.4 degrees. This right here is a huge clue to what makes diamonds so special.
Okay, so we can trap light. What can we actually do with it? Well, it turns out this one principle is used in everything from simple optical tools to the most brilliant and expensive gemstones on Earth. So, have a look at these prisms. They might just seem like simple blocks of glass, but they actually act like perfect mirrors by using total internal reflection. In image A, light comes in and hits the back wall at a 45-degree angle.
Well, since 45 degrees is bigger than the critical angle for glass, the light reflects perfectly, making a sharp 90-degree turn. That's the basic idea behind a periscope. And image B shows how you can use two of those reflections to bend the light a full 180 degrees, a trick that makes binoculars way more compact. The real advantage here is that almost zero light is lost, which makes it way better than a normal silvered mirror. And that brings us back to the diamond. That incredible sparkle, it's a direct result of that tiny critical angle we talked about. When a diamond is cut, the gem cutters are pros at shaping the internal surfaces, the facets, at really steep angles, much greater than that 24.4-degree limit. This traps the light, forcing it to bounce and ricochet all around inside before it can finally escape back out the top. And it's all those multiple internal reflections that create that signature fire and brilliance that diamonds are famous for.
But the single biggest, most important application of total internal reflection, the one that truly shapes our modern world, is fiber optics.
So what is an optical fiber? It's basically a really, really long, thin strand of unbelievably pure glass. It's got a central part, the core, with a high refractive index. And that's surrounded by a layer called the cladding, which has a slightly lower refractive index. Light signals get beamed into the core at an angle greater than the critical angle, and boom, they're trapped. They just bounce perfectly from side to side, zipping down the fiber for miles and miles without ever escaping. And the efficiency it's just mind-blowing. Because the glass is so pure and the total internal reflection is so perfect, more than 95% of the light signal makes it through an entire kilometer of cable. That's how we're able to send massive amounts of data, all our emails, our phone calls, our streaming videos, across entire continents and under oceans. All right, we have covered a ton of ground, so let's just boil this all down into a quick cheat sheet with the most important things to remember.
So to recap, there are two absolute must-haves for total internal reflection. Condition 1, light has to be going from a denser to a rarer medium. And Condition 2, the angle it hits the surface at has to be bigger than the critical angle. We can find that magic angle with the formula, the sine of IC equals N2 over N1. And we see its power everywhere, from the fiber optics that run our internet, to the prisms inside binoculars, to the incredible sparkle of a diamond.
From guiding all the world's data to creating breathtaking beauty, total internal reflection is just one of those fundamental rules of physics with world-changing results. And that kind of leaves us with one last question to chew on. Now that you know the rules for trapping light, what could we build with it next?